All right, welcome to this whiteboard session. Listen up, because today we're shifting gears. If you're used to building standard integrations that just process records one by one, you kind of need a fundamentally different mindset for what we're about to dig into. Handling true enterprise-level volume means you have to stop thinking like a junior developer and start thinking like a lead systems architect. So let's dive right into this explainer and look at how we build systems that don't just work, but scale effortlessly under massive load.
Now, the architectural patterns we're exploring today aren't just theoretical textbook ideas. These are battle-tested, real-world implementations brought to us by the experts at Biz Insight Consulting. They've used these exact blueprints to handle massive data loads without breaking a sweat, and we're going to unpack exactly how they do the heavy lifting.
So, here's our roadmap for today. We'll start by defining the high-volume challenge. Then we'll look at why you need a superior batch scheduler. After that, we'll cover atomic locking and statelessness, how to master partial failures, and finally, smart retries and back-off.
Let's kick things off with Section 1, the high-volume challenge. To build the right solution, we have to actually understand the parameters of the problem, right? We're talking about processing 300,000 to 400,000 sales order line records per hour. Do the math on that for a second. It equates to roughly 83 to 111 records per second. Now, while this isn't exactly a million record scenario, it still far exceeds what a standard Oracle integration cloud setup can reliably sustain if you're pushing records through one at a time. The system will absolutely choke. So how do we prevent that?
Well, it comes down to establishing our golden rule. OIC is the orchestrator. It's not the processing engine. Think of it like a traffic cop. The actual heavy lifting belongs in the data tier. We use the Oracle Autonomous Transaction Processing Database, or ATP, as a massive shock absorber. The source e-commerce system writes records directly into an ATP staging table as fast as it wants. Then, OIC reads from that table at a controlled, steady pace. If OIC goes down for maintenance, no big deal. Records just safely pile up in the database. OIC never crashes under load because it only bites off exactly what it can chew.
Moving right along to Section 2, the superior batch scheduler. Once we have our data safely buffered in the ATP database, how do we actually trigger the work efficiently? This is where you see a huge contrast between a beginner's approach and an architect's approach. A junior dev will immediately reach for the native OIC built-in scheduler. The problem there, it has a minimum interval of 10 minutes. For our volume, that is way too slow. The architect's choice is to use the DBMS scheduler directly within the ATP database. This lets us run database jobs every 60 to 120 seconds, quickly scooping up precise batches of 500 records and pinging OIC via REST to start processing. It's decoupled, it's lightning fast, and it completely bypasses the platform restriction.
And we don't stop there. By pairing that database scheduler with an Oracle Apex user interface, we hand complete power over to the operations team. They can start or stop the scheduler, dynamically adjust batch sizes for peak hours, and check out dead letter queues, all without needing a DBA or touching a single line of code. You aren't just building an integration here, you're delivering a fully manageable operational product.
All right, part 3. Atomic locking and statelessness.
To process 400,000 records an hour in batches of 500, we need to run about 10 to 14 OIC instances concurrently. And concurrency introduces a massive danger: race conditions. When you have 14 instances waking up at the exact same time looking for pending batches, you risk 2 instances picking up the exact same batch, leading to duplicate processing. So what's the magic bullet? For update, skip locked. By using this specific SQL clause, an instance atomically claims a batch. If another instance runs the same query a millisecond later, the database just tells it to skip the locked rows and grab the next available batch. No duplicates, no collisions. Brilliant, right?
And this lock enables a perfectly stateless design, which is absolutely critical. An instance reads its own batch, writes to its own partition, and updates only its own rows. An OIC instance should know literally nothing about what the other 13 instances are doing. All the state lives safely in the ATP database. Why does this matter so much? Because if an OIC instance suddenly crashes midway through a batch, its state isn't lost somewhere in the cloud. Another instance can safely pick up that exact same batch and reprocess it without causing any data corruption whatsoever.
Let's move to Section 4, Mastering FBDI Partial Failures.
This is the target system integration phase. It's where we write data into Oracle Fusion. And honestly, it's where I see the most expensive mistakes being made. Making individual REST API calls for bulk data is a classic rookie error. Pushing 80+ individual transactions a second will strain the Fusion system and practically guarantee you get throttled. True professionals use file-based data import, or FBDI. You transform your 500 records, upload a file, and submit a single ESS import job. Oracle's internal bulk processing engine takes over. And crucially, we don't waste resources constantly polling to see if the job is done. We use a smart callback pattern so Fusion automatically pings a second OIC integration the exact second the job finishes.
Now listen closely here, because handling partial failures is what truly separates the seniors from the juniors. If you send a batch of 500 records and 10 have bad data, Oracle Fusion will successfully create 490 orders and reject 10. You absolutely cannot treat that entire batch as a failure. When that ESS callback hits, your integration must retrieve the detailed error report from the UCM server, read it, and update only those 10 specific failed records in your staging table with the exact error message. Then, you mark the other 490 as completed. You have to handle every single record explicitly.
Which brings us to Section 5, Smart Retries and Backoff.
What happens to those 10 failed records? Designing for failure is never an afterthought. If a network times out, firing an immediate retry is just going to slam your integration straight back into the exact same transient error. You need an exponential backoff strategy. You wait 1 minute, then 5 minutes, then 15 minutes. You have to give the network or the database the breathing room it actually needs to clear the error. If it still fails after 3 attempts, well, it's likely persistent bad data, so you automatically move it to a dead letter queue so it stops blocking up your pipeline.
And at this enterprise scale, we do not rely on humans staring at dashboards, waiting for a red light to blink. We use Oracle Analytics Cloud and set up automated alerts. If your error rate spikes over 5% or your queue depth gets 30 minutes backed up, or say you have 0 successful batches in 5 minutes, the system should proactively alert the operations team before the business even notices a slowdown. So I'm going to leave you with this question to chew on before your next build. Are you just connecting point A to point B and hoping for the best? Or are you truly designing a decoupled, stateless, batch-driven architecture that can absorb massive shocks and heal itself? Apply these patterns, and I promise you, you'll be building like an architect.
And that wraps up our masterclass. A huge reminder that this scalable architecture playbook, from the ATP staging tables right down to the FBDI callback patterns, is brought to you by the experts at BizInsight Consulting, Inc. Thanks so much for joining me on this explainer, and I'll catch you in the next one.